Last week I studied about PLL. It sounds like PLO. PLO. I don't know the spelling and pronunciation, but in some time, in some lectures I had listened, the teacher said like PLL for PLL. PLL is a phase locked loop. Actually, it locked also frequency and phase are locked by this circuit or this topology. And this is my own exercise for utilizing English, how to speak in English, which is rarely happened to my life. So it's very not so easy for me to think in English. But in this reservist textbook, Design of Analog CMOS Integral Circuits, PLL is featured in section 14, 15, 16, 17, 16. And he wrote, this chapter is for the basics. Also, there's another a lot of topics for PLL for various applications, but basically we need to remember. I also think this is memorable, and we must remember this chapter's basic concepts. And even though if we are not the designers for PLL, just utilizing it, or just for user concepts for PLL in applications, we need to know minimum knowledge about PLL, and PLL like PLO, which is like this. I don't know what he or she stressed, like the I didn't remember. I'm not good at drawing a picture in these days. PLO, I don't know what kind of PLO is this. PLO is behavioring, like imitating another genius person, actual person, imitating mimics. PLO is a mimic of the movement or style of some person, and so PLL is a mimic, copy of the generous clock, like crystal. crystal XTL oscillators. Clock is generated. The devices called oscillators or made up of crystal or in these days MEMS clock is famous, and also actual crystal oscillator is used frequently more than enough, and crystal generate clock pulse. Clock is, as we know, this is 4 o'clock. Like indicating the time for usual usage, daily life. We know what time is now by watching the clock. Watch or clock. The clock is the same as this, then counting 1 second, 2 seconds, 3 seconds, 4 seconds, and many times to infinite, almost infinitely counting the time in special frequency, 1 per seconds. One pulse per second means 1 hertz, 10 hertz, 10 to the 6, which means 1 meter is to 1 megahertz per 1 megacycle per second. Pulses are generated by oscillators, circuits, or devices. MEMS is mechanical, electrical, something. Not a micro electrical mechanical system. Recently, nano version is appearing. NEMS is appearing. NEMS clock, I don't know that. Clock generates a pulse, voltage pulse, usually V high to V low, peak to peak. Output from its output. From its output, the pulse named clock is generated. In the sequence in the time, and this is the periods T, 1 cycle, 2 cycle. 1 cycle is T seconds, some usually nanoseconds, picoseconds. So this 1 over T equals F, means frequency, hertz per seconds. So PL has clock generator, and it's oscillating clock voltage, oscillating voltage output voltage, oscillating peak to peak, and the clock generating device usually several decades of several tens of several tenths of megahertz, like 20 megahertz frequency of clock. Now we need 200 megahertz or more, sometimes 2 gigahertz, 10 to the 9th times 2 hertz clock inside the smartphone or circuit board, printed circuit board devices. Of course, personal computer needs gigahertz of clock to calculate operations. Many missions refers but outside of this board, the attached oscillator can generate less than 100 megahertz itself, and we need to multiply the frequency tens or hundreds times. So we need, in a sense, we need PLL here, or PLL used like this. You use generate higher frequency like this, called synthesizer. In this situation, PLL has another jobs to do. PLL. We need PLL for doing synchronize clock, synchronize several clock, multi clock, clock 1, clock 2, clock 3, clock number n in a system, in one printed board circuit, or in one processors. Several clock is with different frequency or same frequency, but in synchronous. Synchronous means like this. This is half the frequency, twice the period of system number 2. But the rising edge or falling edge of these clocks are well aligned in our printed board or processor, MPU or CPU, central processing unit, or what kind of MP. And because we need to arrange many byte of bits, 1 byte 8 bits, bit of numbers 0 or 1 or 0, indicated by 1 volt is what for to 1, 0 volt ground for 0, like from VDD equals 1 volts. High and low signal is arranged in a buffer in parallel at the same time. Their buffer line and latch to the registers, but and they're used to for calculating many operations at a time, in parallel. A lot of numbers, so 1 0 is used for one calculation at a time, and so the CPU or MPB very fast to calculate to their job, but for outside of interacting outside of the PCB, outside of the system, we need interface, very first interface, effective interface. So actually the parallel number bit is exchanged for serial number bits using P2S, like memory FIFO memory, or P2S, SADERS, serial to serial to SADERS, or serial to parallel to serial exchange. Parallel to serial, this is parallel, and in this direction, bit by bit, transferred to this system, parallel to serial, parallel coming in and serially coming out, and this operation is in synchronous motion by more than 2 clocks, with more than 2 different frequency clocks. This is 8 parallel, 1/8 of frequency of clock is used to capturing 8 bit, and 1 F frequency, some original frequency F to serially output, transferring the bits. So there's 2 frequency, but well arranged. To arrange the clock's edge, we utilize PLL also. Neatly arranging the clock edge in different places is very difficult. Then actually there no ideal edge is there. The edge in time always in some time the ideal T0 is not for one edge. It doesn't happen, and you always have the deviation with delta T0. So this is called sometimes jitters. So jittering clock is ideally arranged, but in some error with much less enough error, we can calculate very first a multi-bit of operation and serial interface to transfer the results of the operations, and TX to RX, transceiver to receiver, and vice versa. We use ideally well-arranged clocks utilizing PLL phase locked loop. Of course, these frequencies more than 100 megahertz, usually much more than 100 megahertz in the PCB or CPU, but they are all from one generator, having several tens of megahertz from MEMS oscillator or crystal oscillator. multiplying the frequency, we also use PLL. So, roughly speaking, PLL used in two ways, like that: multiplying and arranging, and get correct data from the system without error. If clock is not well arranged, the bit is once shifted, read one to another. One data is sequence of data is lagged to another one or read to another one. So the calculation is wrongly processed, and we never get the correct answer from computers or cell phones. So we need a good clock to operate, and we use PLLs. So how to multiply and arrange is that I studied type 1 and type 2 PLL. Type 1 PLL is imitating generator input, feed in, which phase is feed in, and feedback in minus, plus, inverted, subtracted input of output phase. Phases compared by ideal reference clock, reference some different time t0 to with some deviation. There's excess phase deviation. Some ideal defined point t or this is phase. This is phase plus excess phase phi e. Phi equal some defined time to the edge or the to express in English or even in Japanese, definition telling the definition of the phases. In actual operation is sometimes very difficult. Maybe different for situation, but like that is a phase, and the phase is reference. Ideally, this is if phi 0 is also phi 0. This is phi in to phi out, and phi in equal phi 0, and phi out finally going to phi 0. The two clock reference and operating clock is well arranged, and in multiplying it, very fast. This is f0 and this is 100 times of f0. I can't really write the here, but the phase is the same. Finally, by the operation by way of the PLL system, near feedback and phi in to phi out approaches 1 in a very long decade. Milliseconds, several milliseconds, in some milliseconds or microseconds. And in this, what phase, oh, there's the phase difference detector. Phase detector is there. PD, phase detector. Phase detector after and phase detector and phase difference is integrated average. Phase difference is output is like this pulse, and this describes this pulse with this correspond to phase difference, and this difference, this PD1, this is the PD2, right? And PD1 is less than PD2. This is average, right? The PD voltage is here. In this case, there, up here. This is PD2 and PD1. The average of these, some defined units of voltage. So PD is pulse, and the integration of the pulse is the output of PD with low pass filter. It has low pass filter of like 1 plus S over omega 0. There's no multiplication, just a filter. One dimensional, or 1 degree, or one pole, just one pole, having one pole or filter in series or PD, and the output, we need oscillator to it with voltage controlled oscillator, because the frequency is arranged attached to equalized to the input clock, so we need to control the frequency with voltage. So in this case we control with voltage, so voltage controlled oscillator is there. Voltage controlled oscillator has a gain of some KVC, K sub VCO divided by S in S plane. And this is multiplied by VCO, KVCO divided by S. And the phase difference is, phase is outputted and the feedbacked. And this has a gain, PD has a gain of KPD. Phase to output is linear, and this is KPD. So this is KPD, phase to phase difference, phase to phase difference. This is V phi in, and this is VI. Phase to voltage is KVD. So type 1 has one pole with S equals 0. One pole. Type 2 has 2 poles where S equals 0. One pole. So one pole corresponding to type 1, this one, And actually this is KPD, and the P in, P out, P in open loop gain is the multiplication in series with this is KPD times KVCO divided by S times 1 plus S over omega 0. Omega 0 is a minus 3 dB frequency of this filter, low pass filter, and this is open loop gain transfer function of phi into phi out of type 1 PLL. Type 2, before type 2, this is open loop, then closed loop gain, this is in small h of s, closed loop capital H of s equals small h of s divided by 1 plus h of s is closed loop, because phi in minus phi out times this gain hs equals p out. So in this case phi out over phi in equals phi 1 plus hs phi out equal hs phi in. So this is going to this in closed loop. Closed loop phi out over phi in is this. So putting this h to z here, we get closed loop transfer function of type 1 PLL. And we know therefore we know this representation, the response of the type 1 PLL phase lock loop. And then what the difference for type 2, I don't know, I can't remember. Maybe there's no low pass filter, but type 2 has charge pump, phase detector is charge pump to transport. Charge pump has K charge pump charge pump gain divided by S, and BCOs here. Type 2 use charge pump features pole at frequency of 0 or omega 0 radian per second, S equals 0, and there are 2 poles at the frequency 0, and the topology is the same, phi in to phi out. So the HS of type 2 equal KPD, KCP, KVCO divided by S squared just. Maybe it is like this. Chargeable. There are sometimes, many times, they need this oscillates, so they need 0 or this kind of loop filter to stabilize the type 2 PLL transfer action. This in this, the phase is delayed 180 degrees. So the negative feedback of this 100 degree with 100 degree with enough gain, or gain larger than 1. Of course, this is maybe PPD, KCP, KVCO larger than 1, and this oscillates without 0, adding of 0 here. So actually they have 0, which is type 2. And just a little bit faster, and adjusting range is wider, maybe. This is smaller and slower because of the low pass filter timing constant. So there's 2 types of PLL, having one pole, 2 pole at frequency 0, omega 0. And next, I would like to represent, calculate the response, step response of omega in to omega out of this type 1. I finished here once,